Here you have the example of chemical ionization. So this is Ci or E high. E high is electron impact. Ci is chemical ionizations. So this is the example of the chemical ionization spectrum of the 3-nitral-benzyl alcohol. Same compound I showed you previously with electron impact. But in that case, this is ionization, chemical ionization. And the gas is the isobutane. This is not the methane, but the isobutane. It means that here you have the two compound, the two product of the isobutane reaction. But I'm very interested by this part. Remember, the mass of my compound is 153 Dalton. And I have here a peak, a molecular peak with 154 Dalton. It is normal because, of course, we have to consider that we have MH+, then I see the mass of my molecule plus 1 Dalton. And then I see 154. If I want to calculate the mass of the molecules, I have to take the mass here minus 1, because minus the mass of a proton. And then the mass of my molecules is 153 Dalton. As I told you, you see that here now you have very small part of fragment. We have a small fragmentation with the loss of an alcohol. So here you have the molecules with the loss of the alcohol with the mass of 136. And here in that case, of course, you can see that we lose a lot of information about the fragmentation. So in chemical ionization, we obtain generally the molecular mass of the molecules and no fragmentation. So we have to choose, depending of our application, if I want to obtain information on the structure, and in that case, I will have the need of electron impact, because I will have the need of fragmentation. And if I don't need that, I just want to have my molecules, my pure molecules, I have to work in the same condition, but in chemical ionization to obtain this information. Okay, let's talk now about another type of source. So the two first source, electron impact and chemical ionization, are linked by the principle of the source. There's only a difference between electron impact and ionization, chemical ionization, due to the presence of the reaction gas, but the schematic representation, the geometry of the source are similar, and on the same apparatus, it is generally possible to perform electron impact and chemical ionization, depending on the parameter. But now I will speak about another source, another principle, a physical principle, which is the well-known electrospray ionization, the ESI. If you go to the literature in mass spectrometry today, you will see that classically you have 90% of the literature speaking about ESIMS. This is the source, the electrospray ionization, because this source is very important in mass spectrometry. This source is a soft source, meaning that this is not possible to perform fragmentation in this source. This is a soft ionization source. And this source is based on the atmospheric pressure formation of charged molecules from a spray created in an electric field. It means that we have a capillary here, a classical capillary in stainless steel capillary, and here you have liquid, and we perform with this source here, we perform in the cathode and the anode a high voltage, a different of potential. If you have a difference of potential, you have the deformation of the liquid to the appearance of a Taylor cone. This Taylor cone, represented here, allows at the end of the cone the nebulization of the compound by a spray formation. Then you have a nebulization cone here. And you can see your compound are here, and you obtain at the end the ionization of your compound. Then, if I show you now with a schematic representation of the process, this is a process in different steps. There is 3 different steps for the formation of the cone. This is the principle of the spray production. Here you have a capillary, okay, filled by a liquid, and it required a flow by a pump at atmospheric pressure. So you have a pump here, and you have a difference of pressure. Okay. If I don't apply any electrical field, I obtain here a droplet, of course, and then we have a droplet at the end of the capillary. Okay. The second step is I have to change the voltage, to apply an electrical field, and then to apply a difference of potential, a voltage. Here you have the application of the high voltage. It is 2000 volts. In 2000 volts, just a reminder that you continue to perform the pumping here at the inlet part of the capillary. If you perform high voltage at the end of the capillary, you see that this droplet change, and we have peak effect that drive the formation of the liquid in droplet loaded. So here you have the deformation of the droplet here. But nothing happens because you see this is not a cone. And if you realize the good voltage, here this is 3000 volts, in that case we obtain at the end of the droplet the emission of a visible spray. This droplet expels dry, start fission, and at the end generate desolvated ions. So the process allows, with the pumping here and the fact that we applied at the end of the capillary a voltage, we obtain a spray, and there are different steps to perform the ionization. This droplet is the compound we want to ionize. This droplet expels dry first, start fission, and generate solvation ion. Here you have the representation of this spray, and you see this is a visible spray. Here you have the Taylor cone represented here. So here this is the needle tip. In that needle tip you have the capillary. The droplet is here, and we have the jet, the Taylor cone, represented by this Taylor cone. Here we have this Taylor cone. After that we have the jet, then the formation of the spray, and here we have the plume corresponding to the desolvated ions.